Good afternoon, ladies and gentlemen, friends of CIC. Welcome to the most important show of the CIC Lunch Talk this month. I'm Albert Chang, Executive Director of CIC. Today, I'm very glad we have two important guests today. Engineer Chris Wong, the Principal Government Engineer of Highways Department, and also Engineer Wes Jones, Managing Director of JAGARD Hong Kong. Today, the topic of the lunch talk is屯門至赤鱲角link. Now, let me tell you something about the background of these projects. In 2008, June, there was a heavy rainfall happened in Hong Kong. And you can see from this slide, on that day morning, the whole North Central Highway was flooded by rainwater and landslide. So the road access to the airport was totally cut off. So it triggers Highways Department at that time to hard push an alternative route to the new airport. And this slide showed about the routing of the屯門至赤鱲角link. So you make use of the man-made island of the Hong Kong-Macau Bridge near the airport to provide a landing point for the tunnel. So after exploring different options for the route, Highway Department decided to use a very deep subsea tunnel. And they go through, as shown in this slide, difficult geological seabed conditions. So you can appreciate how difficult is these projects. So without further ado, let me start the first questions to Chris first. You can see that this屯門至赤鱲角link interconnected with Hong Kong-Macau Bridge and also the existing road network in Hong Kong, and maybe further north to the road network in the Greater Bay Area. So Chris, can you tell us the strategic value of this project?
Okay, thank you, Albert. The屯門至赤鱲角link is divided into the southern connection and northern connection. The southern connection, mostly on viaduct, was opened to traffic in 2018. The northern connection, mainly comprised a subsea tunnel, was commissioned on December 27 last year. The strategic value of屯門至赤鱲角link is multifold. First of all, the 9-kilometer屯門至赤鱲角link provides a strategic link connecting the Northwest NT to North Lantau, Hong Kong International Airport, Hong Kong Zhuhai Macau Bridge, Hong Kong Port. The屯門至赤鱲角link shortens the traveling times between屯門South and the airport by about 22 kilometers. The journey time is reduced correspondingly by about 20 minutes. At the same time, it helps divert the traffic to and from Lantau, thus reducing the traffic load at the North Lantau Highway, Lantau Link, and屯門Road. More importantly, as just mentioned by Albert, the new link provides an alternative road access between the airport and the urban area in addition to the Lantau Link, thus providing a better and more reliable transport structure to Lantau, which is the aviation and land transport double gateway connecting Hong Kong to other parts of the world and mainland cities of the Greater Bay Area. It thus revolves Hong Kong as an international and regional hub. Lastly, the commissioning of the northern connection has created an opportunity for the quota-free scheme for the Hong Kong private car traveling to Guangdong via the Hong Kong Zhuhai Macau Bridge. In Chinese, we call it 港車北上. The Hong Kong SAR government, together with the Guangdong government, is pressing ahead with the scheme. The scheme will facilitate Hong Kong residents to drive to Guangdong province for business, visiting families, or sightseeing on a short-term basis.
Okay, Chris. Understand that the屯門至赤鱲角link is the first subsea deep tunnel constructed by TBM. So there must be a lot of challenges during the construction. Can you tell us some of them?
Yes, it's a very challenging project. The section of the northern connection linking屯門and Hong Kong Zhuhai Macau Bridge, Hong Kong Port, lies across Armstrong Road, which is one of the busiest navigation channels in Hong Kong. The alignment of this section is within environmentally sensitive area. There are also two submarine power cables serving the airport to minimize the impact on Armstrong Road, the habitat of Chinese white dolphin and the nearby marine ecology. Avoid the need to divert the existing submarine power cable serving the airport and eliminate the dredging of and disposal of 11 million cubic meters of marine settlement. A TBM scheme was chosen for the屯門至赤鱲角link subsea crossing in preference to immersed tunnels.
I see. Okay. Now, Wes, just now Chris talking about the challenges. So there must be some very interesting solution to resolve this kind of challenges. As the main contractor, can you tell us something about it?
Sure. Well, as Chris said, we used, for the challenging geology, we used 2 slurry TBMs for the main drives. However, the original scheme also required the construction of traditional cut and cover structures at the north and south approaches in newly formed reclamations. So the additional challenge here was the time needed to construct firstly the reclamation and then this traditional cut and cover structure, both taking quite some time. So we developed a scheme to replace the cut and cover with extended TBM drives, resulting in a much smaller launching shaft and then extended tunnel section up to the ventilation shaft. So this solved some of the problem, but it also created other challenges because the road gradient on the northbound incline was around 3%. Therefore, we needed 3-lane width on the alignment and therefore a very large cross section. So the solution here was to introduce the world's largest TBM, largest TBM. Whilst this overcame the width challenges, it also again created other challenges which needed careful consideration. So how to construct such a huge machine inside a shaft, how to accommodate up to a 560-ton capacity crane, some very challenging constructability issues. So we designed a circular shaped D-wall for the shaft, which is a very stable structure, with strutting needed only at those intersection nodes of the circular elements. So if we play a short video now, you can see in a time-lapse video the assembly of the machine. So you can see the pieces of the shield being installed with the main drive. Then we install the face of the machine, back part of the shield going in, then the segment erector, and then the backup gantries to follow. So you can see here lots of working space and a really good working environment for such large equipment. Then we launched both machines. Particular care needed here, particularly at the beginning where we're got as little as 4 meters of cover, and we end up with 640 meters then of twin tunnel, replacing what would have been a very time-consuming cut and cover structure. So we arrived then at the north ventilation buildings. The next challenge: how do we cross this vent shaft? And at the same time, we have to reduce the size of the large diameter machine because as we get into the subsea section, we no longer need this large diameter. So the first machine, we created a steel bell. You can see to the right of that photo on the right, this steel bell structure filled with concrete. And then this allows the first machine to pass through in a normal tunneling mode. Takes about 2 weeks, where normally probably up to more 2 months. We don't need the very time-consuming construction of the break-in, break-out structures and so on. And at the same time, it allows sufficient space to be able to remove the larger diameter shield and replace it with a smaller diameter. And you can see again the picture on the right, a bit rusty larger diameter shield being replaced at the front of that photo with the smaller diameter.
Oh, okay, great, Wes. Understand that, that the size, as you said, the size of the TBM cut head is the largest at that time in the world. And also because the tunnel need to go underneath the sea, 50 meters underneath the sea level. So it must be very difficult for the workers to go out to do the maintenance of the cut head. Can you tell us, is there any special method to cater for that kind of situations?
Sure. So if you look at the photo on the left here, maybe before talking about specific solutions for that, just a reminder of what it looks like inside the shield of the machine. So you can see to the left, we have the excavation chamber full of slurry. Behind that, we have the bubble chamber where we use the air pressure to moderate the pressure at the face. And when we need to go in to change cutting discs, then we go in through the airlock. We lower the slurry going through the airlock. And then the guys are working in quite a challenging environment to do the necessary maintenance and so on. We also have quite an innovative in-house system called Moby Dick. And this allows us to get real-time monitoring on the geological conditions, the condition of the cutting discs, etc. So you can imagine, though, doing this in 6 bar of pressure because of the depth, it becomes a very, say, high-risk activity and quite time-consuming if you're using traditional diving techniques. So we introduced a saturation diving solution. It's a very sophisticated setup with very specialised team. So we had at peak up to 6 doctors, 3 nurses, day and night shift, and some 45 professionals working in hyperbaric condition. We had to work very closely with the labour department and a lot of liaison and coordination with them. So with this technique, the divers are able to work in much longer working cycles in much safer conditions, and they typically stay in this hyperbaric environment for up to 28 days. And I know you're asking the questions today, but I want to throw one back at you,
Okay.
just to surprise you. Two most important things for the divers when
Yes.
they're working in this environment.
Yes.
Any guesses what the 2 most important things are for them?
Well, I think it must be living within the compressed air conditions, and also how to make sure they're living happy. Yes.
Yeah, exactly.
Yeah.
So the 2 most important things, do I have Wi-Fi?
Yes.
And what's the menu?
I see.
So if we were able to satisfy those 2 requirements, then generally we were able to keep the guys reasonably happy.
Yeah.
So here, we play the first video on the top left, just so you can get a bit of a feeling on how it works. So the guys are inside this steel tube. They get transported down to the machine. Then they launched onto the machine, moved up to the face, connect into the machine, and then they can go about their business, come back, and it's a bit rushed, this video, but you can get the idea. So 28 days living within that on a cycle. And if you just play the video on the bottom right, I thought could be interesting to show, because not too many people maybe have seen this, but this is the working environment in which the guys have to deal. So you can see not easy working conditions, physically demanding, and so you imagine doing that, getting back into your little steel bubble, back to the surface, and doing that in and out for 28 days. Quite demanding role.
Yes. So quite a difficult job, for the workers. Now, in the first slide, we have seen that,屯門至赤鱲link will land at the Manbing Island, the Hong Kong Macau Bridge at the southern end. So there may be some, and because of the Manbing Island, the soil condition is quite special. So, we expect that there's some special method in the construction of the southern connection. Chris, can you tell us what are the difficulties and challenges in that part of the constructions?
Now, in general, the geological configuration along the tunnel alignment is typical of Hong Kong area with a seabed made of very soft, compressible marine deposit over sandy or clay alluvium. Below this layer, highly decomposed granite is found on top of the bedrock. However, on the southern landfall, the ground conditions are particularly adverse. The marine deposit and clay alluvium are very thick and deep. The thickness of this soft material is up to 30 meters. They are up to 50 meters below the sea level. Also, the bedrock is very deep, down to minus 90 mpd in some areas. If we use conventional strictly wall cover dam, we'll still struggle to build this section, a cut and cover section. Cut and cover tunnel, very congested ELS will be required to support the cover dam. We need to control their stability very carefully. Extensive ground treatment will be required to stabilize the whole system.
I see. So, Wes, I would like to ask you, because I was told that there's a special name for that kind of construction. They call it caterpillar. So can you tell us more about this kind of caterpillar type of constructions? I understand this is the world first type of constructions.
Yeah, so probably maybe the longest caterpillar. The principles are quite similar to what we did on the northern end of the alignment, where we had this more peanut shaped launching shaft, much smaller. So here we've extended the length of the design. As Chris said, building a traditional cut and cover in such ground conditions and with such a tight time frame would have been virtually impossible. So we developed this caterpillar design, some 15 cells in length, 432 D-wall panels, and with the obvious advantages of working in a virtually strut-free environment. So much faster to excavate and much faster to construct the permanent structure. Well, however, as is usually the case with these things, it still has its own challenges, and one of the most critical parts of this caterpillar design was the Y panel at the nodes of where the circular shapes are joining. They are transmitting very heavy loads, so they're very large, very heavily reinforced, and quite a complex geometry. So I think we had up to 900 cubic meters in any one panel, some 130 ton of reinforcement, and some very complex lifting operations, sometimes having to use 3 cranes to be able to rotate the cages, and then very heavy craneage, 400 ton capacity to install the cages as well. And probably one of the main risks in doing this, because of the size and the time it takes to construct these panels, probably the biggest risk is around trench stability. And we had to implement certain measures to ensure that we maintain stability in the trench while we're doing the excavation, the installation of the cage, and the concrete pouring, and so on. The other challenge was, so in terms of program, we wanted to be able to break into the shaft with both machines as early as possible. To allow the machines to break out before the excavation of the entire caterpillar was complete, we came up with this scheme to isolate the first 3 cells by introducing a back arch. You can see that at the bottom left of the image. But this introduced even more complex geometry for those nodes. So we came up with this, what we call a half-star panel, and this allowed the first 3 cells to be excavated, the machines to come in, whilst we're still working on the excavation further up the caterpillar. And then just a couple of images here, and I guess the main point here is you can really feel the amount of space that we have to work. So in terms of productivity, the excavation goes much faster. In terms of the construction of the permanent structure, also going much faster. And of course, a much safer working environment, which is probably the most important thing. So a little bit of an aerial drone shot, I think, if we can just play that video. And yeah, so you can appreciate the scale of what was achieved here. Well, of course, there is a bit more excavation overall. There's a bit more quantities in the diaphragm wall panels, but this is far outweighed by the improvement of the safety and of the productivity, and I think that's really the most important thing. Yeah. Okay.
Good. Yes. I also understand that there's a very special features of this project. There is a surface gallery underneath the carriageway within the tunnel for housing those utilities and also for the future maintenance. So it's a very special thing for this kind of chamber in a tunnel under such a deep level of sea, in the sea. So Chris, can you tell us something about any innovations measure that you have adopted for this surface gallery?
Oh, indeed, it's a very, very, very special feature, as mentioned by Albert, to make good use of the space under the tunnel carriageway formed by the TBM construction. The engineering team developed a very smart idea to provide a surface gallery under the tunnel carriageway to house utilities and E&M facilities. Some drainage pipes, fire mains, power supply, and control system for some of the tunnel facilities were installed in the service gallery to facilitate future maintenance. And part of the daily maintenance work can be carried out at the same time during the tunnel operation. This arrangement also reduces the risk of tunnel closure due to emergency repairs. Besides, electrical vehicles are provided for commuting inside the service gallery to improve the efficiency of the maintenance work there.
Okay, thank you, Chris. Now, as you all know that CIC is always very keen to promote DFMA instead of in situ construction because you have a lot of advantage. So, Wes, I would like to ask you, as the main contractor for this project, understand that you have adopted a lot of precasting things instead of in-situ construction to cater, the difficulty in the tight project program. Can you share with us some of your thoughts?
Sure. So as you say, like everything on this project, no exception for the internal structures, a very tight timeline. So we needed to find a way of being able to construct the internal structures as soon as possible, following as the machine is progressing through the drive. I guess looking at the project, given the length of tunnel, given the repetitive nature of the structures, also taking into consideration that we had direct marine access, it was really the perfect storm to be able to apply the principles of DFMA, and we use the terminology DFMA, but I guess in infrastructure we've been using precast for quite some time, and here we were able to really maximise the amount of precast construction for all of the internal structures. So if you look on the right there, you can see the bottom in the invert of the tunnel, there's a service gallery, precast, the parapets either side of the service gallery, precast, the OHVD slab on the top, precast. So the only piece left that we had to do in more traditional in situ works were the two corbels on the sides of the tunnel. And I'll talk a bit later about future opportunities to introduce innovation in constructing those elements as well. So just to show a couple of videos here. So first of all, maybe you can play this video. Yeah. So you can see here the gallery arrives on a truck, put into place. We have a bespoke tool which is used to lift up the element, install it into position, and then lower. So we needed to have a tool which was able to provide a ramped access from the elevated height, the top of the gallery, down to the tunnel invert, and do that as quickly as possible without interrupting the logistics and supply to the back of the machine. And you'll notice in that video as well, there's very few workers, so much more efficient and much safer way of carrying out the works. The other example on the OHVD slab. So again here, we needed to find a quick and safe way of installing these elements. Maybe we can play the video and I can talk to that. So again, the elements arrive. They're lifted up by a lifting device which was designed with our sister company VSL. We install that into position. You can see we're able to maintain the access through the tunnel while this work is ongoing. And again, not too many people involved in having to do this work. You can imagine a more traditional OHVD slab with scaffold everywhere and false work everywhere. So much more efficient, much safer way of carrying out the works.
Thank you, Wes. So other than DFMA, I understand that in this project, you have applied a lot of the opportunity for using robotics. The robotic is another thing that CIC is promoting to help them in the quality and then time constraint problem. So can you tell us something about the robotic applied in this project?
Sure. So if you go back to that video I played earlier, thinking about that video I played earlier where the guys are working inside the cutter head, how difficult the working conditions are and so on. Within the company, we've been working on this solution for nearly 10 years now. It's called Telemac. And the idea here is, again, to improve the safety, to improve the working conditions, and to improve the efficiency in how we work. So it's a robotic arm which is located inside a dedicated airlock. You can see on the bottom left there, the blue arrow. There's a dedicated airlock here where this robotic arm is positioned. On the right, you can see a sketch of what it looks like. If I go to the next slide. So the idea here is that the robotic arm, it's in 3 stages. The first step is to inspect the location. It has this stereophonic laser vision, inspect the location, position itself. If necessary, it's able to clean with water jet the environment. Then it goes in, it's able to remove the worn cutting disc, put it in a console, pick up a new one, and then install it into position. So again, I think there's a short video here. If we can just play that video. it's a little bit slow, but you get the idea. And I guess so. It's an ongoing development. One of the limitations here is that it takes up quite a bit of space. So we need to be doing this in large diameter machines in the order of, I would say, 12 meters or above to have the space to do it. And the other limitation, for the time being at least, is that the location of the airlock is only at the periphery of the machine. So whilst this is where we have most wear in the cutting discs, it doesn't allow us to be fully robotic in this operation. So with this scheme still, ongoing improvement, but there are still some elements which require human intervention. And again, I'll talk shortly about another innovation that we're going to introduce into Hong Kong, which overcomes this, this challenge. So, yeah.
So this is about the robotics
So
that you
that's,
apply
so
in
that's
that
the robotics
project.
on that project.
Wow,
yeah.
very impressive. I'm sure that, the audience, really, very enjoying knowing about, how you apply the robotics in these projects. So with your experience and your insight, so in future similar construction projects, what do you think? What would be the robotic application and also other innovations, that you can think applicable in the future?
Yeah. So again, thinking back to what I mentioned about the corbel being the only element of the internal structures which still today is being done in situ, our next development, which we're going to introduce into the Trunk Road T2 project, which is currently ongoing, is to have some robotic arms on one of the back gantries of the TBM. So this will allow us to do a lot of that high-risk, laborious activity, scabbling the face of the lining, drilling and installing anchors and so on. So this will take out one part of the traditional way of constructing these corbels, but not the entire step. So there's a little video again here, I think, to play, just so you can get the idea. So these will be mounted on the gantry, as I said. We're able to scabble the face, prepare the surface, drill the anchor holes, and this takes out this what would otherwise be quite a risky working at heights operation. And then, well, step by step, the next challenge for the teams, not for this project, but in the future then, is to find a way, I think, of trying to be able to construct maybe with some kind of horizontal slip form or something of this nature, where we can actually be extruding the construction of the corbels as we progress with the TBM drive.
Right. Okay. Thank you, Wes. So I think today, just now, both Chris and also Wes has shown us, some special features of the projects. So maybe not enough to you, but because of the time limitation, I think now let's have a overview video of the whole project first, and after that video, we will have a short time that we can answer any question if raised by the audience.
Yeah, sorry, maybe just before you go, because there was
Okay.
one more. Sorry, there was one more.
Right.
There was
Sure.
one more new innovation which I wanted to share.
All right.
with you.
Okay. Why not?
So as I mentioned, the robotic arm, very innovative, but some limitation in the in how much of the face it can cover. So again, on this Trunk Road T2 project, we're going to bring a new technology into Hong Kong, which is now, I would say, ready to be used, and that's what we call an accessible cutter head. So it's a new technology, but it allows all of the cutting discs to be replaced in atmospheric conditions. So we don't need the guys to go into the face, as we saw in that earlier video, and we're able to achieve this using individual airlock chambers at each of the disc locations. So, yeah, much improved working environment. No need to go into hyperbaric conditions, so no need for this saturation diving and so on. So, well, it's new to Hong Kong. It's very exciting, and we will hopefully have an opportunity to come back maybe at a later time and share that when we have a bit more feedback.
Thank you, Wes. Now, as I said, let's have an overview video of the project. Then we have a Q&A section after that.
屯門and Chep Lak Kok was separated by sea. To get through, we need a direct connection. The屯門至赤鱲角link. Go straight, go forward. Hong Kong, one of the busiest cities in the world, renowned for its top-notch infrastructures. The new屯門至赤鱲角link further enhances the city's transport network, bringing convenience to our daily life. The屯門至赤鱲角link northern connection includes a sub-sea tunnel connecting northwest New Territories with the Hong Kong-Zhuhai-Macau Bridge Hong Kong Port and the Hong Kong International Airport. The southern connection includes a viaduct linking the Hong Kong port and North Lantau. The link not only shortens the journey between屯門and Lantau, but also diverts traffic from the Lantau link, relieving traffic load for road networks in both areas, and offers new possibilities in travel and living. Journey time between屯門South and the Hong Kong-Zhuhai-Macau Bridge Hong Kong Port, as well as the Hong Kong International Airport, will be shortened from half an hour to 10 minutes. It enhances the airport and the Hong Kong-Zhuhai-Macau Bridge as transport hubs and provides connection to the Greater Bay Area and the rest of the world, creating endless opportunities for the city. The屯門至赤鱲角Tunnel is the longest and deepest subsea road tunnel in Hong Kong, approximately 5 kilometers in length. The project is marked by enormous scale and sophisticated construction process. The project team overcame various challenges by employing expertise throughout the design and construction process. Innovative technologies were adopted for tunnel construction, including saturation technique and caterpillar cofferdam. Tunnel construction at 60 meters below sea level was unprecedented in Hong Kong and posed tremendous challenges to the team. The project team deployed the world's largest tunnel boring machine with a diameter of 17.6 meters. It is as tall as a 6-story building or 4 double-decker buses stacked together. This method greatly reduced excavation and sediment disposal and helped protect the environment. To perform excavation at such depth, the team had to overcome a hyperbaric environment with up to 6 times the normal pressure on land. The team made history by adopting saturation technique and pressurized living chambers, unprecedented in Hong Kong. This minimized the need for decompression procedures and ensured the health and safety of hyperbaric workers. The team also applied other innovative technologies, such as real-time surveillance of boring machines and remote-controlled machineries and robotic arms to reduce manual labor under hyperbaric environment. To increase efficiency, huge amounts of precast units were used, which greatly reduced the number of on-site labor. Installation was easy and time-saving. It also improved the working environment. The southern landfall adopted innovative caterpillar diaphragm walls as temporary retaining structures, creating larger working space for constructing the cut and cover tunnel, and saved construction time and increased efficiency. Unlike conventional tunnels, the屯門至赤鱲角Tunnel is the first in Hong Kong to include service gallery beneath its carriageway, facilitating maintenance in the future. A strategic link with improved connectivity adds impetus to economic development and offers greater convenience to travelers.屯門至赤鱲角link. Go straight, go forward.
Now, let's start the Q&A sections. From the audience, I received quite a lot of questions. I just select a few to answer. First question from the audience is talking about the client project management and also design course. So, Chris, I mean, what can you tell us about this kind of cost in the whole projects?
Well, I think the project management cost is a very tiny portion of the whole projects, but we have to ensure that the project is properly managed, ensure we have good safety performance, ensure that the project is delivered on schedule, and to ensure that we deal with all the environmental issues properly.
Okay, thank you, Chris. The next question is about construction, about the DFMA, and why use the off-site precast prefabrications rather than in situ. So in general, maybe Wes can just highlight more on what are the advantages of DFMA in these projects compared with the traditional method of constructions.
Sure. Well, we probably touched a little bit on that during the presentation, but the most important consideration we have when we're thinking about how we're going to execute the works is for the safety of our people. So this is the primary consideration, and I think applying the principles of DFMA really helps us to address this priority. So that's the first point. DFMA is safer than traditional construction methods. You can, well, as the name says, you design the elements of whatever it is you're building to be built off-site and then to be assembled in a more controlled manner on the site. And in the case of屯門, we had these specific tools to be able to help us to do that. So safety is the primary consideration. The other main consideration also is the program. And we mentioned a few times during the presentation, the overall time frame for this project was very, very tight. So by doing all, and particularly the internal structures, we're able to have all of these elements being constructed much earlier, and then delivered. As I mentioned during the presentation, we have direct marine access. So this is another consideration. If you have a project perhaps which doesn't have such easy logistics and access, it may be something to think about with other solutions. But here we have the direct marine access. We can get in much earlier, and it really helps to secure the program. And I think also we shouldn't forget that it also brings a much higher level of quality to the works. All of those elements being constructed in a more controlled factory environment ensures the very highest quality is achieved, and then coming to site, again, just putting them together. So safety, program, and quality, I think, are really the main considerations when we think about DFMA.
Okay, thank you, Wes. Thank you, Wes, and also thank you, Chris. I think our time is nearly up, so I have to close this Q&A sections. All you all agree that this afternoon, we have very good information about the special feature of the屯門赤鱲角project, which is a very important and very impressive project so far in the Hong Kong construction industry. So thank you for your attendance of this lunch talk, and I would like to thank you, Chris and Wes, once more. Thank you for coming and sharing with us of this important projects. So please, do pay attention to our CIC lunch talk in the next coming weeks. Okay, thank you very much.